Hello everyone, thank you for visiting our poster. My name is Cheon-ho from Jeonnam-daeju University in South Korea, Computer Vision Lab. Today I will be presenting CSF-Net, a context-semantic fusion network for large mask painting, accepted at WACV2026. Brief overview. Image inpainting is the task of restoring missing or corrupted region in an image with content that is visually coherent and semantically consistent with the surrounding context. As shown here, given a mask image, the goal is to fill in the missing area naturally. This has broad application in photo editing, object removal, and scene reconstruction. Here's the core for our work. When dealing with large mask, existing state-of-the-art methods suffer from a critical problem, object hallucination. As the mask increases, the available surrounding context becomes insufficient, causing the model to generate content that looks structurally and semantically incorrect. On the left side, you can see the mask input and result from existing method. On the right side, our CSF-Net generates a semantic guidance image that provides strong structure priors, leading to significantly more coherent painting results. Our approach has three key contributions. First, semantic guidance. We leverage a model completion to provide strong object-level semantic prior for the missing regions. Second, CSF-Net architecture. We propose a transformer-based fusion frameworks that unify texture queue and semantic prior to generate a semantic guidance image. Third, seamless integration. CSF-Net improves existing painting models as a plugin modules, requiring architecture modification to the base model. Let me explain our overall architecture. CSF-Net consists of three stages. Stage A, we generate and select structure-aware candidates using a model completion. Stage B, we fuse contextual and semantic features through dual stream transformer encoders and a cross-attention filter decoder. Stage C, we perform hierarchical pixel selection to construct the final guidance image, I-guide, which then fed in any existing painting model. Let me explain stage 1 in detail. Given a masked image, we first apply a pre-trained model completion model. This model generates multiple object completion from the visible segment in the masked image. Its completion serves as a structural hypothesis for what might exist in the missing region. Here you can see the actual A model completion result. Each visible segment is completed individually, producing diverse candidates. Some completion are realistic, but others are semantically inconsistent with the visible context. This is why we need a filtering. To filter out inconsistent candidates, we evaluate its completion using a combined consistency score. This score combines MSE for pixel-wide similarity and LPIPS for perceptual similarity. Candidates that are structurally or perceptually inconsistent with a reason receive lower scores and are filtered out. Filtering with select the top P most consistent candidate. After filtering with select the top P most consistent candidate as semantic prior for the fusion state. In our experiment, P equals 3 achieved the optimal balance between diversity and quality. In stage 2, we introduce our context semantic fusion transformer. We use a dual encoder architecture. The context encoder processes the masked image to extract contextual cue. The semantic process the selected candidate to extract semantic priors. The fusion decoder then integrates both features through cross-attention. Context features serve as queries, and semantic features serve as keys and values. This enables the model to reason about what contents belong where in the missing region. In the final stage, we perform hierarchical pixel selection. For each pixel in the mask model determine which candidates provide the most plausible content. We use two complementary scoring networks, the structure score network for structure plausibility, and the perceptual score network for textual. At each pixel location, we compute a confidence score for every candidate using both networks. These scores are refined across multiple scales using learnable coefficient beta. Finally, the candidate with the highest confidence score is selected, and its pixel value replaces the mask pixel through the final guidance images. Here are our qualitative results integrated with 4 different baselines. Across all mask types, CSF-Net produces sharper and more structurally coherent results. It reduces hallucination while maintaining visual realism. Looking at the quantitative results, CSF-Net achieved the best performance. The results confirm that our approach is model agnostic and universally beneficial. Our ovulation study showed that combining MSE and LPIPS is more effective than using either alone. P equals 3 achieve optimal performance. Using too many candidates introduce noise and degrade performance. To summarize, CSF-Net is a transformer-based fusion framework for large mask painting. It provides semantic guidance and integrated seamless with existing models. Thank you for your attention.